Swayam Prabha. Digital India. Educated India.
Okay, welcome back to lectures on advanced calculus for engineers, and this is lecture number 23. We'll be talking on exact differential equations. So here is the content. First, I will define what are exact differential equations, how to check whether a given differential equation is exact or not, and then what are the solution techniques for solving exact differential equations. Well, so in exact differential equation, if m and n are functions of x and y, so there are two functions here, m and n of x and y, then the equation this m dx plus n dy is equal to 0 is called exact if there exists a function of two variables again f x y such that this differential of this f x y is equal to this left hand side of the equation m dx plus n dy. So, what is the advantage of having such a function and why do we call this exact? Because here we have the exact differential. The whole differential equation can be written as the exact differential of a function f x y, then we call such a equation as exact differential equation. Meaning is that df over dx is basically partial derivative with respect to x dx and partial derivative with respect to y and dy. This is the differential of f, and this must be equal to m dx plus n dy, because once we have this df x y is equal to 0, then we can easily find out the solution of the given differential equation. So, the whole idea is how to find this f x y, because once we have d f x y is equal to 0, then we can integrate simply and we will get f x y is equal to c as the solution of the given differential equation. So, what are the necessary and sufficient conditions for a given differential equation to be exact? So, the necessary and sufficient condition for the differential equation m dx plus n dy is equal to 0 to be exact is del m over del y is equal to del n over del x. So, that is the only condition here for the exactness. This is necessary and sufficient. That means, if the given differential equation is exact, then this relation must hold. That means, partial derivative of m with respect to y must be equal to partial derivative of n with respect to x, or other way round, if this relation holds, that means the given equation is exact. Okay, so, just to see to go through the proof of this. So, first we will show here that the given condition is necessary, meaning that if the equation is exact, then we will show that this relation holds. So, if the given equation is exact, that means this f x dx f y dy must be equal to m dx plus n dy as per the definition of the exactness. And now we can equate the coefficients of dx and dy. So, here the m is equal to this f x and this n is equal to f y, the partial derivative of f with respect to y. So, assuming that f is continuous up to second order partial derivatives, and indeed which we can easily assume, because here we are assuming anyway that these partial derivatives exist, and we have to also assume that these are continuous. So, in that case, when we take the derivative of these equations, so for instance, if we take here the derivative of this m with respect to y, so del m over del y will be equal to del 2 f over del y del x. And since we assume the continuity of these derivatives, that means this will be equal to the other mixed derivative, that means del 2 f over del x del y, which we can write as del over del f del over del x of del f over del y, and the del f over del y is basically n. So, this here we have this partial derivative with respect to x and then with respect to y is del n over del x. And therefore, what we got here that del m over del y is equal to del n over del x, that is the condition or the necessary condition for exactness. That means, if the equation is exact, if the given differential equation is exact, then del m del y must be equal to del n over del x. Okay. So, now we go here to show that the given condition is also sufficient condition. That means, if that condition holds, then the equation is exact. So, this is little bit lengthy to prove, because here we assume that del m over del y is equal to del n over del x, and then we will show that the given differential equation m dx plus n dy is equal to 0 is exact. That means, we need to find a function f x y, a function of two variables, such that the exact differential of this function f is equal to m dx plus n dy. So, we need to search now, we need to find that what is this function, whether such function exists or not, whose differential is equal to m dx plus n dy. So, to construct this function, we first of all we define this g x y as the integral of m dx. So, it is a partial integration of m, that means, we will keep y as constant and we will integrate this m with respect to x, and this function of x y we are denoting as g x y. That means, partial derivative of this g with respect to x will be m. So, that is the relation, that del z over del x is equal to m, or g x y is equal to integral m dx. So, first we show that this n minus del g over del y, this term here n minus del g over del y, this is a function of y only. So, how to show that this is a function of x only. So, we will integrate here, we will differentiate this n minus del g over del y with respect to x and see that this is 0. That means, this is a function of y only, there is no x term involved here. So, del over del n from here minus del 2 g over del x del y, and assuming the continuity of the partial these mixed order derivatives, what we get del n over del x minus del 2 g over del y del x. So, this is equal to del n over del x minus del over del y of del g over del x, and del n over del x minus del over del y, del g over del x is basically m. So, we have here del m over del y, and this is equal to 0 because this is the condition we have assumed. That means, if we partially differentiate this n minus del g over del y, that is coming to be 0. That means, it is free from x, it is a function of y alone. So, now we consider this function f, and it is constructed with the help of this function g, which was defined as integral of m dx. So, we consider now the function f as g x y plus the integral of this n minus del g over del y with respect to y, and we claim now that this is the desired function, this is the function we are looking for, whose differential will give us exactly m dx plus n dy. So, that is to be shown now. So, we will show that df is equal to m dx plus n dy. Well, so what do we have? We have f, which we claim that this is the function we are looking for. It's it's a g xy plus this integral n minus del g over del y dy. So, the differential of this f will be the differential of g plus differential of this term. So, we will compute now the differential of g. We know the definition for the differential. This is partial g over partial x dx, partial g over partial y dy, and plus what we have here again the differential of this function, and with the same definition. So, the partial derivative with respect to x of the function plus into dx plus the partial derivative with respect to y of this function again and minus del g over del y dy and into this dy. So, this is now has to be simplified. So, what do we see, or we note that this n minus del g over del y is a function of y only. So, here if this is a function of y alone and here we have integrated with respect to y. So, whatever comes here after integration, that will be again a function of y only, and we are differentiating here with respect to x. So, this term will go to 0. So, we have only these 3 terms now. Okay. So, we have del g over del x dx, del g over del y dy, and then here also we have partial derivative of this integral which was with respect to y. So, as a result we are differentiating of this integral. This will become only the n minus del g over del y, and which is multiplied by this dy. So, that means n dy and minus del g over del y multiplied by dy term. Okay. So, then once we have this, we also know that del g over del x is equal to m. So, del g over del x is m, we have m dx, this and this gets cancelled, and then we have here n dy. So, what we have shown that this df, the differential of this f is equal to m dx plus n dy, and that was the aim. So, again in the construction of f we need g, and g was nothing but the integral of m with respect to x. So, this is basically the integral of m with respect to x. So, we have m dx integral and plus the integral n minus del g over del y, and we need to integrate this with respect to y, and note that this n minus del g over del y will be a function of y only. Okay. So, the given differential equation is exact. So, we have seen now that this condition is necessary as well as sufficient. Okay. So, now just a remark here, the solution of an exact differential equation, that means m dx plus n dy, that is df is equal to 0. So, as I discussed at the beginning also, if the equation is exact, that means we can write df is equal to 0, and now once we have df is equal to 0, the solution will be simple as f is equal to some constant, because we are just integrating now this one. So, df is equal to just a constant there. So, f is equal to c, that will be the solution of this df is equal to 0 differential equation. Again we note that during that necessary and sufficient condition in the proof, we have realized that f was this m dx, the integral m dx, and the integral of n minus del g over del y dy, and this term was just a function of y alone. So, this can give us a direct approach to find out the solution of the given differential equation, because if we m and n are given. So, if we just integrate this m dx, and here this n minus g, actually this is nothing but these are the term of n not containing x, because here n we are subtracting something and then we have proved that this is a function of y alone. That means we will consider from n those terms which do not contain x, only those terms we will consider which are purely depend on y, and they should not depend on x. So, if we take only those terms of n which do not contain x and then we integrate this and set is equal to constant, that is another or the alternative of just finding this f. We can write directly the solution from the given differential equation. So, we will discuss both the approaches. So, suppose here we have the equation x square minus 4 x y minus 2 y squared dx, and this is n here with dy. So, m is x square minus 4 x y minus 2 y square, and n is given as y square minus 4 x y minus 2 y square, and here this del m over del y. So, if we differentiate this m with respect to y, we will get minus 4 x from here, minus 4 x, and with respect to y. So, we will get also minus 4 y from here. Similarly, if we differentiate this with respect to x, we will get minus 4 y from here and minus 4 x from there. So, this del m over del y is equal to del n over del x. That is a necessary and sufficient condition for exactness. So, this condition tells us now that this given differential equation is an exact differential equation. The equation is exact. Now, if the equation is exact, there must exist a function f x y such that whose differential, total differential must be equal to del is equal to m dx plus n dy. So, now from here we can get del f over del x as m, which is x square minus 4 x y minus y square, and we can also relate here del f over del y, which is equal to n, and n is given as y square minus 4 x y minus 2 y square. So, we have these two equations. So, having these two equations, now we need to get basically f. So, from the equation number 1, so from this equation what we do, we integrate with respect to x just to write down f from here. So, f will be then x 3 by 3 minus this 2 x square y and the integration of 2 y square. So, that x will be there. So, minus 2 x y square, and then a constant c1 which can be a function of y now, because we are integrating with respect to x and here we are dealing with two variables x and y. So, here it is not just a constant, but we have to write a more general constant of integration, and in this case it will be c1 y. Now, we have this f and we have also del f over del y, another relation given to us. So, what we can do out of this f, we can differentiate with respect to y and then set equal to y square minus 4 x y minus 2 y square. So, here we have del f over del y is equal to, from this equation, the 3 x square. So, with respect to y, so that will become 0, here minus 2 x square, here minus 4 x y, and then the derivative of this c1 with respect to y, and this we can set equal to y square minus 4 x y and minus 2 x square. So, here this minus 2 x square and 2 x square will be cancelled, also this 4 x y will be cancelled, and we will have c1 prime y is equal to y square, and that is the key here, that this process will automatically give you this differential equation which will have only y, because if there is there cannot be x here, because here we have d c1 over d with respect to x. So, dC1 over dx is equal to y square. So, now if we integrate this, so C1y is equal to y cube by 3, and then we have there one more constant. So, yeah, so this C1y means the derivative of C1 with respect to y only, that is the meaning of the derivative. So, we integrate this and C1y will be y cube by 3 plus C2, and once we have this C1y, we can substitute here in the f. So, what we will have, that f is equal to C3, that will be the solution. And what is f now? X3 by 3 minus 2x square y minus 2xy square, that will be our f with this C2, and this C2 and C3 will merge and we can write another C there. Indeed, we have multiplied here by 3. So, this 3 and this 3 can be removed there, and we have this solution x cube minus 6xyx plus y cube is equal to C. Well, so this is the process to get the solution. So, we have the two equations. We will have two equations just by equating this total differential is equal to m dx plus n dy, and by integrating one we will get f, and then we differentiate here. So, we will get del f over del y, which can be made equal to the given function del f over del y, and from there we can get C1 prime y is equal to y square. From there we will get C1 y is equal to y3 by 3 plus a constant, and then the solution f will be equal to C3, which is given here. Well, the direct approach can also be used. So, we have here m dx plus n dy, and the direct approach was the integral m dx, and the integral here dy is equal to a constant c. So, here m dx, so m dx means directly this term we will integrate, and plus the terms of n not containing x. So, that is the only term y square. So, here y square, this does not contain x, here x is there, here x is there. So, we will take just y square, and then dy is equal to constant. So, now we can integrate this. So, here we will have x cube by 3, we will have then 2x square y, and here we will have 2xy square plus here y3 by 3 and is equal to a constant term. So, this is the solution which we already achieved before by finding that f explicitly. Okay. So, here we will show that this differential equation is not exact, and hence it cannot be solved by the method discussed before. So, just to check, first del m over del y is equal to del n over del x, and we will realize that del m over del y is 3x plus 2y, and del n over del x is 2x plus y. So, these two are not equal, hence the given differential equation is not exact. And now, if we follow the approach which we have done in the previous example, we were trying to find f there. So, what will happen if we apply the similar technique here, where we will find the problem. So, here the del f over del x, if we set equal to m for instance, and del f over del y we set equal to this n there, x square plus x y, and try to get f out of it. So, what will happen then? So, here the f will be where we will have this general constant C1, a function of y, and then its derivative with respect to y, which will be related to del f over del y as we have done before. But now, what we will see here, so that this C1 derivative y, which should be a function of y alone, here we are getting x and y both. So, here we cannot integrate this, because this is d C1 over dy is equal to this one. So, if left hand side everything is a function of y, right hand side also should be function of y. So, this approach will not work here. Well, so thus we cannot find f x y such that whose total differential is equal to m dx and dy. For what value of k the differential equation, this is the given differential equation, becomes exact, and then find the solution of the exact differential equation. So, again here we have m and we have also n, and we know the necessary condition for the exactness. So, for that we will compute del m over del x, del m over del y, that is k. So, m is here and this is n. So, m dx plus n dy. So, m is 3x square plus k e power y, and here we need del m over del y, which will be just k e power y, because this will be 0. So, we have k e power y, whereas del n over del x will be 4 e power y, and this will be 0 because this is y and we are computing here with respect to x. Now, these two must be equal for the equation to be exact, and that means this k must be 4. So, for this value of k, that is 4, the equation becomes exact because we have the condition of the exactness. Hence, the given differential equation is 3x square plus 4 e power y, that is m dx, and then we have here n dy. Now, we need to find the solution. So, we can use that shortcut approach, the direct method here. So, m dx, so we will integrate just this function here, 3x square plus 4 e power y dx, and then plus out of this we will get those terms which do not contain x. So, here only this 3y square does not contain x. So, here 3y square dy is equal to c, and then we integrate this, we will get the solution x cube plus 4x y e power y plus y cube is equal to c. That is the solution of the given differential, exact differential equation for this value of k. This is the last example. Check if the following differential equation is exact. So, del m over del y, if we compute del m over del y here, we will get only 2y, because all other terms are just x, and here also 2x. So, x square plus 2x, the derivative will be 0, and then here we have n, and del n over del x in this case is 0. So, one is 2y, another is 0. So, the equation is not exact because del m over del y is not equal to del n over del x. So, the given differential equation is not exact. Now, what we realize that suppose we multiply the given differential equation by this e power x, what will happen to the differential equation? So, our differential equation will become e power x, then we have x square, then we have y square, plus we have 2x dx, and there also we have 2y and e power x, and we have dy is equal to 0. This is the new differential equation if we just multiply both the sides by e power x. And now, if we check this condition, what is our del m over del y in this case now, because e power x is also multiplied now. So, that will be 2y e power x, and what will be del n over del x now, because with respect to x we have to differentiate, that e power x will be as it is. So, 2y e power x, and now what we see that after multiplying the whole equation by e power x, the equation becomes exact, and so del m over del y is 2y e power x, and del n over del x is 2y e power x, and therefore, the equation becomes exact now, and such a multiplier or such a function which we multiply to the given non exact differential equation, and then differential equation becomes exact, we call such a factor, such a multiplier as integrating factor. And that will be the topic of the next lecture, where we will find that how to find such an integrating factor for the differential equations which are not exact. So, just to conclude here, the necessary and sufficient condition for the exactness of the differential equation is del m over del y is equal to del n over del x, meaning that if the equation is exact, this condition must hold, or if this condition holds, then the equation will be exact. And once we know that the equation is exact, that means there must exist such a function f x y whose derivative or whose differential, the total differential, is equal to exactly m dx plus n dy. Or once we have found this f x y, then f x y is equal to a constant will be the solution of the given differential equation. The solution will be just f is equal to c. We have also seen that the one approach would be kind of the direct approach, where we will try to find out the f by equating df is equal to m dx plus n dy and getting the relation of the partial derivatives of f in terms of m and n. But there was a shortcut approach as well, where we can find the solution directly. That means, if we integrate here m dx, keeping this y constant of course, and here we need to find the terms of n which do not contain x, and those terms only we will integrate here, and everything should be set equal to that constant, and this will give us the solution. This is a direct approach for finding the solution. So, here we have the references which are used for preparing this lecture, and with this I thank you very much for your attention.